In the next couple videos, we're going to consider a few more types of diodes. In this one, we're going to look at a light emitting diode, or an LED, and I'm sure everybody has probably at least heard of LEDs, even if you weren't really familiar with exactly what that meant. So now we're going to relate it to sort of what we know about our semiconductor physics and our diode. So for a diode in general, we know that if we have a forward bias diode, we're going to have some current, because remember, we're sort of counteracting that built-in barrier across our depletion region, and we have current flowing. So if we have current flowing, remember, for our p-n junction, that means our carriers are moving out of our depletion region. So carriers move out of depletion region. And so what that means is once they go out of that depletion region, remember, this is a minority carrier device. So then we have minority carriers, which are going to be recombining. So for instance, if we look sort of at our simplistic structure here, so if we have our P and our N, and we have some electron which has managed to get over here, of course we have more holes in our P region than electrons, and so ultimately that electron can find a hole and it can sort of fill the hole, and in doing so this process is called recombination, and our electron and our hole sort of disappear, so we get rid of both of them. So what that looks like in terms of our band gap, of course we have our conduction band edge E sub C, our valence band edge E sub V. So let's say we have some hole down here, and we have some electron in our conduction band. So let's say this is in our p-type side. And so if this comes down and it recombines here, then what's going to happen is there's going to be a photon released. And so of course this photon, if this band gap energy is appropriate, can be in the visible spectrum, and then we can have a colored LED. So a couple sort of qualifiers to that, though, and a couple comments to make, is that we need to have direct band gap materials. So we need this special type of material called direct band gap. So we can't just make LEDs with any material. It turns out silicon is actually not one that we can make LEDs with. An example of a direct band gap material would be gallium arsenide. And so this is again something that's a little beyond the scope of our text, but for those interested, basically you can look into something called K-space, and it ultimately refers to whether or not our momentum of our electron has to change as it's moving from our conduction to our valence band. So the sort of opposite of direct band gap is we cannot use indirect band gap materials. And so an example of that would be silicon. So of course silicon is a very common material, but because it's indirect band gap, we can't use it for LEDs. Something that I sort of alluded to a little earlier is, of course, we know this is some known energy, E sub G, our band gap energy. So this E sub G is going to determine energy of the photon. So let's just say this is sets energy of our photon. And so ultimately what that means then is it's setting the wavelength of our photon, which is related to the color of the light coming out. And so basically what that means is that by selecting an appropriate material and maybe engineering a material a little bit, we can get certain colors based on the band gap.